Okay. So we are in the middle of our result about the goodness of uniform convergence, right? So uniform convergence and differentiation, right? And we don't have such a nice result, but we have at least the following that says that if you have a bunch of, if you have a sequence of differentiable functions, if you have a sequence of differentiable functions, and their derivatives converge uniformly on AB, and there's some point in AB where the sequence itself converges. Okay. Then in fact, the Fn actually do converge uniformly. On AB, right, to some f, to some function f. Okay, that f turns out to be differentiable to some differentiable f. Okay, and the derivative of that limit function turns out to be the limit of the derivatives, right, for all x. Okay, so that's the theorem that we are in the middle of proving. We had proven the first part, that Fn converges uniformly to some function f. We hadn't seen that that function was differentiable. So we haven't proven that it's differentiable. We're going to now prove the second part, that it is differentiable and its derivative is what you hoped it would be, right? That is, and this is basically, again, a commutation result. You're saying that when you take the limit and then differentiate, it's the same as when you take the derivatives first and then take the limit, right? That you can change the order, and that's not true. That's not true in general. Okay. So all of this should be in your notes from last time. So let's just go on to step 2. This is step 2. So we already showed that these guys converge uniformly, and now we're going to show that our claim is that f prime x equals limit of fn prime x as n goes to infinity. Okay, so I'm going to rewrite this as I'm going to rewrite this in the following way. So, well, no, first I'm going to just write this out. What does this mean? Right? This is the limit as t goes to x of f of t minus f of x over t minus x. Right? This thing on the left here, right? So I'm just going to rewrite the statement. Okay? The limit as n goes to infinity of the limit of fn t minus f of x over t minus x as t goes to x. Okay, so this is what we want to show, right? This is what we want to show. Yeah, Max.
At the very end, should it be f and x?
Yes, thank you. Okay, so this is what we want to show, right? Does this look familiar? I see the answer is no. It should be yes. Okay, so this should be very familiar to you because it's almost exactly the same. So let me call this thing phi of x. Okay, let me call this thing phi sub n of x. Okay. Now, right? So let me call this thing phi of x. Let me call that thing phi sub n of x. Now it should look very familiar. We proved exactly this theorem, right? Right before we showed the interaction of uniform convergence and continuity, right? We used this theorem to show that uniform and continuity work well together. That the uniform, if you have uniformly convergent sequence of continuous functions, that they converge to a continuous function, right? You remember that result? And right after that, I gave it to you as an exercise. On the second day, I gave it to you as an exercise, and you proved it very, very simply, right? At that time, you probably were wondering, why didn't we just prove it in this simple way, rather than getting this general result and then applying it to the case of continuous functions? The reason is, we're going to use it now. Okay, we're going to use the general theorem now. Okay, so our general theorem said that if these guys converge uniformly to this, then this statement holds. Okay, that was a theorem from a week ago, way back when. So in order to use the previous theorem, if we have the phi sub n converge uniformly to the phis, then the statement is true by the previous theorem. Okay. So observe, notice that phi sub n converges to phi pointwise, right?
How are we noticing that?
Well, what are the phi sub n's? Right? The phi sub n is this thing, right? And the phi sub n's we already showed converged uniformly to the f's, right? So we're done. Right. So these guys converge pointwise. So it suffices. So by the previous theorem, so by the earlier theorem. Suffices to show that phi sub n converges to phi uniformly on AB. Okay. Okay. So as usual, we use the Cauchy criterion. We'll use the Cauchy criterion. Okay, so right, we want to control phi sub n minus phi sub m, right? Phi sub n minus phi sub m. We want, so given epsilon, we want n such that n and m exceeding n implies that phi sub n x minus phi sub m x is smaller than epsilon for all x in AB. Yeah?
Would it be phi sub n of t or x?
I think it's t.
Oh, I'm sorry, it is t. Yeah, yeah, I'm sorry, this is so wrong. This is phi sub n of t.
Yeah.
Thank you. You saved me. Yes, thank you. Maybe that's why it didn't look right. Yeah. Right? That's
Maybe,
right?
hopefully.
Like, oh yeah, it's the professor's fault. Yeah. Yeah. If only I'd written that as T, then he would have been like, oh, of course. Okay. Okay. So actually, let me write this as T because it should be T also. Right? Because x is some fixed point, right? X is some fixed point in AB. What am I, crazy? Okay. Okay, so what are we going to use? We're going to use the uniform convergence of the Fn prime. So since Fn prime converges uniformly, we know that there exists an n such that n and m exceeding n implies that Fn prime of C minus Fm prime of C is less than epsilon for all C in AB. Okay. So just think, if we look at this phi nt minus phi mt, well, that is fnt minus fnx over t minus x minus fmt minus fmx over t minus x. Right, which I'm going to, you can of course write as fn minus fmt minus fn minus fm of x over t minus x. Right, but what do you know about this sort of thing? Right, this is the slope of the function of this difference function between 2 points. Right? The slope of the difference function between 2 points. Is there some relation between that and the derivative of that function?
Mean value theorem.
The mean value theorem, right? We know that this is going to equal Fn minus Fm prime C somewhere, right? For some C between T and X. T and X. Right? By the mean value theorem. Right? Right, the mean value theorem says that if you have two points A and B, then the slope between the endpoints equals the slope at some point between. Right? So that's all we're saying here. The slope between the endpoints equals the slope at some point between. Okay. Okay. But we said, because of uniform convergence, we know that that is smaller than epsilon. Okay. Uniform convergence gave us that the slope of the difference is as small as we want, right? So we make it smaller than epsilon, and that makes this difference, this slope smaller than epsilon. So that's the end. Right? We get uniform convergence, and we get that that these limits are equal, which proves at the same time that your function was differentiable at that point. Right? That your function was differentiable at that point, and that the derivative equals the limit of the derivatives. Yeah, Larry.
Professor, couldn't we have proved this? So after the f prime n c minus f prime m c part, couldn't we have rewritten f prime n as limit of f n nt minus f nx. Like, couldn't we have written f prime in the form of limits and then solved it somehow? Yeah. I mean, we can rewrite f prime and c as the limit of.
No, because this c, no. So I guess you're saying that, suppose. Yeah, no, it doesn't follow. It wouldn't follow so cleanly. It doesn't follow directly from there.
Okay.
Yeah. Okay. Any other questions? Okay. So this is actually not so bad. I hope you think this is not. I hope you see that this is actually not too awful a proof, right? You say, okay, right, what we need to show is that this thing is small, right? We need to show that this thing is small. Well, this thing is this, right? And once you see this, then you see that it's just a matter of using the mean value theorem, right? The main fact that you use to prove this step, mean value theorem, right? So you say, by the mean value theorem, we know that this is controlled by this. And by hypothesis, we know that we can make this as small as we want. Yeah, Edward.
Can you explain why phi sub n converges to phi pointwise?
That's because we had in the first part that the f sub n converged to f pointwise, right, uniformly.
Okay.
Right. So, phi sub n is just this. Phi sub n is this.
I see.
Right. As n goes to infinity, you're going to get f minus f.
Okay.
Right. There's no. You might be thrown off by these limits here, but phi sub n is just this finite quotient here.
Cool.
Yeah. All right.
So it was the mean value theorem that allowed us to say that fn minus fm prime of c is equal to that thing?
Yeah.
And then how do we know that that's less than epsilon?
Because of uniform convergence of the fn primes, right? The fn primes converge uniformly, so that gives us this thing here, right? So it's this fact that we use to get here, right? So if you want, so star, which by star gives you this epsilon here. Yeah, Thea.
Is it a problem that phi sub n is not defined as x?
No. And see that is what the previous theorem, why we needed that the statement of the previous theorem. You remember in the statement, x had to be a limit point, right? The function didn't need to be defined at x. That function had to have the x was a limit point of the domain of that function, so it doesn't matter. Yeah. So if you're wondering at that time, why are we creating this sort of general function where the function doesn't even have to be defined at that point? This is why. Okay, let's go on. So we're going to do something that is equally fun. That is to create a continuous nowhere differentiable function. So yeah, the proof was kind of fun for me, but I see that it maybe wasn't for everybody. We're now going to do something that is just as fun. It's the creation of a continuous non-differentiable function. Okay, and I think this is, I'm almost 100% sure that this is due to Weierstrass. Weierstrass is the hero in this time period, basically. Yeah, I was once ridiculed at a party for not coming up with Weierstrass as the hero of mathematics during this time period. Like, like somebody came up to me, a mathematician. I just arrived at such and such university, and we're at a faculty party. So and so, who I don't even know, comes up to me and says, "So, who is the most important mathematician of such and such time period?" I'm like, I'm thinking Weierstrass, and I'm kind of shy to say it. And he says, "Pah, Weierstrass," and he calls somebody over. He says, "This guy, wouldn't say Weierstrass." This guy didn't answer Weierstrass to my question as to who was the most significant mathematician in this period of time.
Is that what all math parties are like?
They're all fun in this way. Yeah. Okay. Okay. So. Yeah, so Weierstrass is continuous no differentiable function, which really, really upset a lot of people, because people thought that, well, if you have a function, it's basically a curve, right? It's going to be, at least if it's continuous, it should be differentiable, right? So there was periods of time where people were, not quite clear on certain ideas, right? And they're like, okay, well, maybe it has to be, piecewise differentiable if it's continuous or something like that. But then Weierstrass comes up with this thing that's continuous and differentiable nowhere, right? And this was kind of a shock at the time. Okay, so the construction is pretty cool. Here's the construction. So you start off with this function, which the absolute value function. Okay, but you truncate it to have its domain only between -1 and 1. Okay, so you have this guy, right? -1, 1, right? And it stops there. Okay, but then you extend it, extend to a periodic function. Period 2. Okay, so you say, okay, I'm going to extend it. I'm just going to keep on copying it. I'm going to copy it like this, so that every time I take a point and add 2 to it, I get the same value, right? If I have this point, I have this point, well, my values are the same. So I'm just going to keep on, I have multiple. I just keep on going forever, right? I extend this function in a periodic manner. So it's a simple exercise to see that if you take the difference, phi of s minus phi of t, it's less than or equal to s minus t. Okay, that is basically that the slope is always less than, of absolute value less than 1. Right, between any 2 points SMT, I mean, it's trivial, right? Between any 2 points SMT, the slope is always, whatever 2 points I take, the slope is always less than 1 in magnitude. Okay, so that's what this is saying. This is what's called a Lipschitz continuity condition. So it's Lipschitz continuous. So if, okay. Okay, and this being Lipschitz continuous implies continuity. In fact, it implies uniform continuity, which was a problem on your exam. Okay. Okay. So now we define our function. We define f of x as summation of 3/4 to the n times phi of 4 to the n times x. So n goes from 0 to infinity. Okay. Okay, so what's happening is that we are speeding up time 4 times, right? So it will be like this. Right, the first guy here, right, phi 4x is going to look like this. Right, you've sped up time 4 times, and then you multiply it by this constant. Okay, right. So this guy, what I've shown you here is phi 4x. Right. What we had before. So here is phi of x. Right. Here's phi of x. And then phi 4x is like this. Phi, 4 squared x would be even faster, 4 times faster, and so on and so forth. Okay? But for each of the guys, we multiply them by a decreasing constant. Okay? So we don't add on the full guy. We add on, we take this faster guy, we multiply it by 3/4 to the n, and then, n is 1 in this case, and then add it on. Okay, and then we take the next guy, which is even faster, but we scale him by 3/4 squared, right, and add that thing on. Okay, and then we keep on adding those guys we take an infinite sum of those guys. Okay, now this series converges uniformly. This series converges uniformly. Why does it converge uniformly? Can anyone tell me? Or can anyone tell me the name of a test that we have that deals with the convergence of series? Weierstrass test, right? Weierstrass test, which says that if you're, what does it tell? Can anybody remember? It says that if you have a bunch of functions, and they're all bounded by some constants, and the sum of those constants converges, then your series converges uniformly. Okay. Well, these functions are all bounded by 1, right? So the product of this is bounded by 3/4 to the n, right? This thing is bounded by 3/4 to the n. Summation 3/4 to the n converges, right? And so this thing converges uniformly. Okay. So this converges uniformly by Weierstrass. Weierstrass m-test. Where here m sub n is going to be 3/4 to the n, which certainly is a geometric series when you sum it. I've never told that story about being ridiculed at a party before, but I guess I was embarrassed to say it. Now I don't care. Okay. Yeah. That's all right. Yeah. Okay. So our claim is that this f, well, we know that this f is continuous, right? Because we have uniform convergence. All these guys are continuous, right? So it's a continuous function, and now we're going to claim that f is nowhere differentiable. So here's the proof. It's kind of a cool one. Pick any x in R. Okay. For each, we do something a little bit peculiar. For each m in n, so we pick some x. Okay, we pick some x. And for each m, natural number m, we let delta sub m be defined as plus or minus 1/2 4 to the negative m.
Plus or minus means both?
No, so I'll tell you how we choose the plus or minus in just a second, okay? Where plus or minus is chosen so that no integer lies in between 4mx and 4 to the m x plus delta m. Okay, right? 4 to the m times delta m has magnitude a half, right? Right? 4 to the m times delta m has magnitude a half, right? Has magnitude a half, right? So if we look at 4mx and this guy, well, the distance between them is a half, right? So we've got these 2 points, 4mx and 4mx plus delta m, and the distance between them is a half. So if there's an integer in there, we choose the other guy, right? If this guy was the plus, right? If this guy was the plus and there's an integer in there, then we choose the minus, and there's not going to be an integer in there, right? Because there's only going to be one integer in this interval, right? So we choose. So we look at this, right? We look at this thing here, and we say, where's the integer? If it's here, we choose minus sign, right? If it's here, we choose plus sign. So we choose the plus or minus so that there's no integer between these two numbers. Yeah, Lara.
How do we know that 4 to the power m delta m is the magnitude is half?
Well, delta m is this thing here, right? Right. So multiply it by 4 to the m, and it's plus or minus a half. Okay. So that's how we choose. That's how we choose these deltas. Okay, and these deltas are going to be key to seeing that that the derivative doesn't exist. Okay. So consider 4x plus delta m minus f of x over delta m. Okay. We'll see that this actually exceeds 1/2 3m to the 3 times 3 to the m plus 1. Okay. So that prevents us from it being differentiable at x, right? The limit as we let our difference go to 0, well, there's always going to be these delta m's there, right? There's always going to be these delta m's, which mess up, at which this quotient gets higher and higher and higher, right? And so that messes up our limit. Okay. Okay, that's the problem. Or the solution in substance. That's how this thing is going to work out. Okay, so I'm just going to rewrite this thing as summation 3/4 to the n phi 4 to the n x plus delta m minus phi 4n x over delta m. Okay. 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 So, right. So our m is fixed right now. M is fixed. You think of m as some fixed number, and our n is varying, right, from zero to infinity. So we divide it into 3 cases. If for n bigger than m, if n is bigger than m, then 4n x minus 4n delta m minus 4n x. I'm sorry, phi of 4n x minus 4n delta m minus phi of 4n x. Well, you see that this guy, n is less than m, right? N is less than m. I'm sorry, n is greater than m, excuse me. And so we've got 4 to the n times this thing, right? So we have at least one extra power of 4, right? So that extra power of 4 interacts with the half. We get at least 2. We may get 8, right? We get some power of 4 times 2, right? In other words, we get an even integer. Yeah, Eric.
Why the minus sign? For
That's a plus sign. Sorry. Thank you. Okay. In any case, this thing, whatever it is an even integer. Right? It's an even integer. And so by periodicity, we get 0. Right? This thing has period 2, right? So adding on something, some multiple of 2 doesn't change the function. This and this are the same, we get 0. Right? So we don't have to think about most of these terms, right? We only have to think of the terms m and below. Okay. Now, if n is less than m, then, well, we look at this thing, phi of 4dnx plus 4dn delta m minus phi of 4nx over delta m. Well, what do we have then, right? This is going to be less than 4 to the n. Right? Because of the Lipschitz quality, right? Right? So look, right? This difference on the top here, right? This difference on the top is less than the difference of the arguments, right? And so we get 4 to the n delta m. We're dividing by delta m, and so we get 4 to the n. Right? By Lipschitz continuity.
Why are we dividing by delta m?
You'll see in a minute. Yeah. I mean, I could have divided by delta m up here and still get the 0. Okay, I'm gonna divide by delta m one more time. That's actually what we want because we're trying to control this thing here. Right. So, okay. And if n equals m, then we get phi of 4nx plus or minus a half minus phi of 4nx over plus or minus 1/2 4 to the minus n, 4 to the minus n. Okay, so Right. So what's good about that? remember how we chose this, chose the plus and minus? It's so that there's no integer between these two terms. Okay, so that means that we're back over here. We're either between here and here, or we're between here and here. Right, wherever we are on this function, we're either the 2 points are between here and here, or between here and here. The slope is either 1 or the slope is -1. Okay, so right, so what do we get? Right, we get plus or minus a half over, right, over plus or minus a half 4 to the negative m. That's just 4 to the negative m. 4 to the m, or 4 to the n. Right? The slope is 1, right? The slope is 1 or -1, and we're traveling a half distance, right? So the difference is going to be a half, or plus a half, or minus a half. Yeah, okay.
Are you using the mean value theorem?
No, no. I'm just using the fact that this function looks like this.
Oh, okay. Can you try to explain that one more time?
Sure. Yes. Yes. Okay. So. Okay. Let me do a better job with it. Okay. So we have these 2 points, right? This point and this point. And we know that between these 2 points, there are no integers. Okay, so that means that we are right. We are somewhere on this function phi. Remember, phi was our periodic extension. Okay, we're somewhere on this function, and we are between 2 integers. Right. Right. We are between 2 integers. I'm sorry, there are no integers between us. Okay, so look at the picture here, right? The slope is 1, or the slope is 1, or the slope is -1, right? So let me move out this 4. This thing is either this quotient is either 1 or -1, right? This is the slope, right? You take the function at this point minus the function at this point, and divide by the distance between those points. That's the slope. The slope is going to be plus or minus 1. So I'm taking the absolute value. I take the absolute value plus or minus 1. I get 1, right? And so I end up with 4 to the n, aka 4 to the n. In that case, let me just call it m because that's what I want it to be. Sorry to explain it poorly the first time there. Okay, okay. So remember what we're going for. We're trying to see that this thing is big. Right? Okay, so let's look at it. Well, so then, if we look at this thing, summation n from 0 to infinity, b 4s to the n, phi for the n x plus delta m minus phi for the n x. Everything divided by this guy. Okay. Let me call this term here gamma sub m. Okay. So we saw that if n is bigger than m, then we get 0. So I'm going to just write this as the sum from 0 to m, right? All terms bigger than that are 0. Okay. And now I'm going to pull off the mth term. The mth term is going to be 3/4 to the m times this guy, which we saw was 4 to the m, right? Times 4 to the m. Right? This is the mth term. Right? So of course that's just 3 to the m. Okay, I'm going to erase it. Okay, this guy's just, I'm not going to erase it. It's 4 to the m, 3 to the m. Okay. Right? Okay, and what else do we have? We have the sum of terms from 0 to m minus 1 of 3/4 to the n times gamma sub n. Okay, so we have this 3 to the m, right, minus these guys here. Okay. Now, how big could this thing be? Right? I'm sorry. Let me write it this way. Sorry. We have this thing plus this thing, right? Okay. Now, how big could this thing be? At its largest, we think gamma sub n, right, are at biggest 4 to the n, right? These guys, the absolute value of the gamma sub n, so the absolute values of the gamma sub n's are less than or equal to 4 to the n, right? Okay, so I'm going to use the reverse triangle inequality and say, okay, well, this is greater than or equal to 3 to the m minus this thing from n equals 0 to n minus 1. So I use the opposite side of the triangle inequality, I get this, right? Okay. Now, the biggest that this thing could be is, right, the biggest that this thing could be is if all these guys are 4 to the n, right? If all these guys are equal to, if I take all these guys to be 4 to the n, I see that the size of this thing, 3/4 and gamma sub n, is less than or equal to summation of the absolute values, so 3/4 to the n, 4 to the n, from n equals 0 to n minus 1. Okay. Right? Right? In other words, the sum of 3 to the n from n equals 0 to n minus 1. Okay. So, right? So this thing, sorry to rush a little bit, this thing is bigger than 3 to the m minus summation 3 to the n from 0 to n minus 1. Okay. And if you work that out, that turns out to be 1/2 of 3 to the m plus 1. Yeah, Susan.
Can you explain again how we got from plus sign to a minus sign there and equal to greater than?
So this is the triangle. This is the reverse triangle inequality, right? That if you have a plus b, it's greater than or equal to the difference. Okay, so that's what I'm using here. That this is bigger than or equal to this, right? But this thing at its biggest, and then I'm going to take this thing as big as possible, basically, right? And so taking this as big as possible means that it just gets smaller.
Right. Okay.
Okay, it just gets smaller, and then you get this thing. Okay. So what does that show you? That shows that no matter how how far in you get. You've got your function, right? You've got your function, and it's really crazy looking, right? Right? No matter how close you get to your point, there's always points where the slope is huge, right? There's always some point nearby, x plus delta m, where the slope is getting bigger and bigger. Okay, no matter how close you get, right? No matter how close you get, there's always some delta m nearby, and as you get closer to that x, the m's get larger, and so the slopes get steeper and steeper and head off towards infinity. The slope of the secant lines becomes unbounded, right? And so you can't have a derivative. Okay, that's it. Okay, let me hand back some. Well, no. Do you have anybody have an immediate question?
Are those the ones we just had
Where are your homeworks? Oh yeah, thank you. Okay, let me hand back some homeworks and exams if you're not here last time.